Hello everyone. In this video, I will introduce the multivariable first derivative test in mathematical analysis, which serves as a generalization of Fermat's theorem to multivariable functions. I will first give some background, then state the key theorem, and give a proof. I will also give an example and conclude with a summary. Pierre de Fermat originally proposed his method in a collection of treatises titled Maxima et Minima. The method was later acknowledged by René Descartes, who accepted its validity in identifying maxima and minima. Let's look at the key theorem. Let O be an open subset of Rn that contains the point x0. And let f from O to R be a function defined on O. If x0 is a local extremizer and f has partial derivatives at x0, then the gradient of f at x0 is the zero vector. To prove this theorem, we only need to do a little bit of manipulation of f. Using what you are already familiar with, the first-order derivative test in single variable calculus. Without loss of generality, assume that x0 is a local minimizer. That just means in a small ball centered at x0, fx larger than or equal to or the fx0, no matter which direction you go. Left, right, up, down, or diagonal. F doesn't decrease around x0. So how do we translate this into conditions on the partial derivatives on f at x0? Here's the key idea. We freeze all variables except one, say the ith variable, and define a new function, git. This function gi is a slice of f. It tracks how f behaves just in the direction of the ith coordinate, holding everything else constant. By the definition of the partial derivative, we know that gi is differentiable at t equal to 0, and gi prime 0 equal to f partial xi x0. And here comes the crucial insight. Since x0 is a local minimizer of f, then each of these slice functions gi also has a local minimum at t equal to 0. Now we apply a powerful tool from single variable calculus, the first derivative test. You may recall, if a differentiable function has a local minima at a point, then its derivative at that point must be a 0. So since gi has a local minimum at t equal to 0, we must have gi prime 0 equal to 0. That gives us a beautiful conclusion. The partial derivative with respect to xi must be 0. And since this argument works for every coordinate direction I equal to 1, 2, to n, we conclude that the gradient of f is 0. So, in sense, what we did was reduce a multivariable problem to a series of single variable problems. And we used the first derivative test, something familiar and intuitive, to reach our conclusion. Now, let's return to the theorem. Someone may ask if the gradient of f at x0 is 0. Does that mean x0 must be a local extremizer? It is a great question. And the answer is no. To see why, let's look at a classic counterexample. Consider the function fxy equal to x squared minus y squared. By computing, its gradient is 2x and minus 2y. At the origin, we have the gradient equal to 0 and 0. But is the origin a local minima or maxima? Actually, it's not an extreme at all. Let's zoom in on a small open ball around the origin. For any small radius delta larger than 0, consider 2 points within that ball. U equal to R0, V equal to 0R. Then we compute Fu equal to R squared, which is larger than 0, and Fv equal to minus R squared, which is less than 0. This means that the origin is not a minimum or a maximum. Actually, we call this point as saddle point. It sits right at a turning point in every direction. By looking at this figure, we can see this more intuitively. And this is why it is called a saddle. By determining whether a critical point is a minimum, maximum, or saddle, we will need to look further, typically using the second derivative test. At the end of the video, let's make a summary. The multivariable first derivative test is not only of theoretical importance in mathematical analysis, but also plays a vital role in practical optimization problems, where it serves as a necessary condition. The multivariable first derivative test provides a straightforward way to locate potential extrema of a multivariable function. It tells us that any local maxima or minima must occur when the gradient is 0. Once these critical points are identified, further criteria such as second derivative test can be applied to distinguish between maxima, minima, or saddle points. If there are certain constraints, for example, the variables must satisfy a given equation, the same idea can be continued via Lagrange multipliers. We look for points where the gradient of the objective function agrees with the gradient of the constraint function. This simple yet powerful principle has a wide range of applications in machine learning, operations research, and so on. That's all for the video. Thank you for watching.